Hydrolysis, hydrolysis of salts. Salts are ionic compounds which are formed in neutralization reactions. So an acid plus base yields a salt in water, right? Salts can be characterized from the type of acid and base which combine in the neutralization reaction. Salts can be formed from the reaction of a strong acid and a strong base, a strong acid and a weak base, a weak acid and a strong base, or a weak acid and a weak base. We are not going to worry about this one so much, but I want to give you some relationships here. So if I form the salt NaCl, what would be the parent base that gives me the Na? NaOH, sodium hydroxide. All right, how would you classify this, as weak or strong? Why? Group 1. All right, so this one is going to be a strong base. All right, what would be our parent for the chlorine ion as an acid? HCl, hydrochloric acid. Would you classify that as strong or weak? Strong. So if I make that reaction, what pH would you expect in the end? A strong acid and a strong base? Neutral. You're going to expect a pH of 7. All right. So let's look at a different combination. Let's look at NH4 NO3. All right. So breaking this apart, this NH4 ion, what would be its parent? It was a proton acceptor early on, so it's going to be a base. So what base would NH3? All right. Ammonia. Ammonia. And then this one, its initial situation would have been nitric acid, HNO3. So ammonia, is it classified as a weak base or a strong base? Ammonia is weak. All right. It has a very high pH, but it's a weak base as far as the way it does. And HNO3 is a strong acid because it has 2 more oxygens than it does hydrogens. All right. So in this case, what kind of pH would you expect? A pH greater than 7 or less than 7? Less than 7. All right. And then let's look at one more. We have sodium carbonate. So we looked at this one earlier. What would be the parent for sodium? Where does the sodium come from? Sodium hydroxide. And then the carbonate, what acid would this come from? HCO3, carbonic acid. All right. Now, sodium hydroxide, we already classified that as a strong base. In this one, looking at this, will we classify it as a strong acid or weak acid? Weak. Because it's got carbon in it, and the other thing is there's only 1 more oxygen than there is hydrogen, so that's going to be a weak acid. All right, so as far as pH, what pH would you expect in your end result? Greater than 7, less than 7, or 7? Greater than 7. All right. Now, today, what we want to be able to do is calculate the real pH of it. This is just kind of the oversimplified baby way when we don't really want to do any work with rice tables and all of that. So let's kind of move forward and look at some things. There are some slides included that you can read that goes into greater detail about this material than what I want to talk about right now. So I want you to find an area where you can write some stuff down. I went on the page where you have this top part that says talking about 2 ions produced in aqueous solution, and then right before it says doing hydrolysis calculations, I've just used this space. So I want to go back to my compound Na2CO3. All right. We know that this is a salt. It's a product that comes from an acid-base neutralization reaction. We have a metal or a positive ion, and then our polyatomic negative ion, anion, and it combines to form that salt. So what we want to look at is if I were to write a dissociation reaction for this, if I'm dissociating this into its ions, what ions are going to be produced from this? So so that's the 2 ions that are produced. Which one of those comes from, so looking at this in terms of net ionic and all of that, if we look at the sodium here, if we just took the sodium, 2Na plus H2O, what's going to end up happening is this would form sodium hydroxide, and then I'm not going to balance it, I'm just kind of showing you what's happening here, and then H2 gas. You've all seen this reaction, remember? Well, most of y'all have seen it. I dropped a little piece of sodium in the water, it fizzles around and produces some gas, and then you have a new product. All right? But what you need to see is if we break this down into net ionics, the sodium becomes a spectator and it kind of disappears. So it doesn't really help us see anything. So we're not going to focus on the strong, we're going to focus on the weak parent. Or we're looking for the ion that comes from the weak parent. And let me erase that and actually make it look like it says weak. From the weak parent. So this is the one that we're going to use in our rice table. So we're going to take that ion. So I have my little rice table here. I'm not going to actually solve an equation with it. I'm just showing you the setup. So I'm going to take my ion from my weak parent, CO3 negative plus H2O, and this is my hydrolysis reaction. What is that CO? It's basically a reverse Bronsted-Lowry reaction. What is my CO3 going to do? What does it want? It wants a hydrogen. So it's going to form carbonic acid plus what? OH negative. Now, this OH negative presence is what makes it basic. Makes it the base. So, you would go ahead and go through there that you have whatever concentration here. This concentration is going to go down. these two concentrations are going to go up, and you have your N thing in your rice table. Ultimately, that's what we're going to look at. So it starts with the I based on the ion of the weak parent. So you're always looking for which one forms the weak acid or weak base. And that's the one that you're going to write your reaction from. So let's kind of look at this in context. Those slides that I included, you can read those on your own. It'll expand further. But for time's sake and everything, let's just go ahead and look at some problems. All right. Number 12 says predict the products when KCN is added to water. Will the pH of the solution formed when the salt is added to water be greater than or less than 7? So let's just kind of break it apart. K is going to come from what base? Yours. Did you get the packet that I gave out yesterday with the full? All right. All right. So what is going to be the parent base for the potassium? KOH. Is that strong or weak? Strong. All right. So are we going to be worried about the K at all in this? No. Our CN is going to come from what? HCN. All right. So now all I really need to do is disassociate this. So my dissociating reaction is KCN is going to disassociate into K plus CN negative. And I want that one for my reaction. So and all this is really asking is will the pH be greater than or less than 7? So now we're going to show that we have CN negative plus H2O, and we're going to look at what's formed. We're going to look at the ion that ends up in the product side. So we end up with HCN, so cyanic acid plus OH negative. So what does that OH negative in the product make this an overall type of solution? Basic. So basic solution, which means that pH will be greater than 7. That's all you have to do to answer that question. All right. These are going to be kind of oversimplified questions, and I'm just building this up to the real ones. All right. So number 13 says write the dissociation equation that happens when amine chloride is added to water. All right. Amine chloride is a salt. So we want to find out our two roots. So we have CH3, NH3, Cl. The dissociation reaction is just going to break it up into its ions. So it's kind of like a ionic, net ionic or whatever. So what we know that the Cl is going to form a negative ion, right? And that means that our amine group is going to be our positive ion. And it doesn't matter which order you write it in. We just know that that Cl is our anion and the other group is our cation. that's all you have to do for that one. Number 14. I don't want you to do this part of it. All right. Write the equation which describes the acidic character of CH3 NH3 plus. All right. This one already kind of did the things for you. You don't have to worry about breaking up the salt or anything like that. It just kind of gave you the information. So we're just going to take our weak ion, or our ion from our weak parent, and figure out what acid and what base was originally there. So adding it to water, H2O. We know it's weak, so it's going to be equilibrium. So this is a positive, so it's probably going to do what to that extra hydrogen? It's probably going to lose it, so we're going to go CH3 NH2, and now that goes from being positive to 0. And then how does that change the H3O, which becomes positive. So after this reaction, the overall solution is going to be, has a higher presence of H3O, so that means it's going to be acidic. So it produces acid in solution. All right. Now, number 15 is where we're really looking at one of the problems. This one we're going to need a rice table and all of that. All right. So we are looking at this compound right here. NaC2H3O2 is our salt. The reason why we know it's a salt is because it has that metal cation and the polyatomic anion. I don't remember what this one, I think this one is acetic acid. No, sodium acetate is what it is, I believe. So this is our salt. This is acetic acid right here. You'll need this information later. I'll show you where the info came from later. All right. So I don't need you to actually show the dissociation reaction all the time, but I do want you to know what ions are going to be produced from this. So we're going to produce two ions. We're going to produce a sodium ion. That's going to be Na+, and we're going to produce an acetate, C2H3O2. Which one of these ions is coming from the weak parent? The carbon-based one. That's the one that's going to be important. So we're going to set up our rice table. So the acetate will be the important ion here. All right. So I'm going to take that ion, C2H3O2. I'm going to add it to water. And I'm going to react it. It's a negative ion, so it wants to gain a proton. So that's going to become C2H3O2. That should not be a negative there. Plus, we lose a hydrogen from water, and so that becomes OH negative. All right. From our problem, we had a concentration of 0.700. Water doesn't matter. And our initial concentrations of these two are 0. It means this is going to subtract. This is going to add. and that's going to add. So 0.700 minus x, x, and x. All right. We can trump our x, so we can drop that. We're going to go ahead and establish our equation, but notice that we have Ka equals OH negative. All right, so since we have that OH negative in our product, what is this overall solution? It's going to be basic, but we have a Ka. Ka is for what? Ka is for acid. So we need to find a relationship between Ka and Kb, and I'm going to give you that in just a moment. All right, if you flip back a page, I actually flip back 2 pages, and right above where we were writing, and look down at the bottom of the page, we see that Ka times Kb equals Kw. What does Kw equal? 1.0 times 10 to the negative what? 14. So since we have a Ka and we know Kw, we can say that Kb is equal to Kw over Ka, which would be equal to 1.0 times 10 to the negative 14 over whatever our Ka is. So that means that I can set up my equation, and I'm going to come down here to the bottom to set it up so that I have room. So I'm going to take this. I'm going to set it up. So I'm going to say 1 times 10 to the negative 14. I'm just going to put it all in one problem. Over my Kb, which was 1.8 times 10 to the negative 5 equals x squared, that times that, over 0.700. And then I solve for my x. So see what y'all come up with. Yes, Kw is the constant for water. Water is considered to be the neutral substance, so acid times base on that is going to equal 14. .97. Is there a E on that?
Yeah, to the negative 5.
All right, so that's our X. Then and that is a concentration, that is mole per liter. So since we have mole per liter of hydroxide, what can we calculate directly from that? Can we calculate pH directly from that, or we can calculate pOH? So negative log of 1.97 times 10 to the negative 5 gives us a pH of what? pOH of what? 4.7. So our problem is asking for the pH, So pH is going to be 14 minus POH. 9.3. All right. All right, for numbers 16 and 7, for number 16, A and B are actual problems. C is not an actual problem. But let's go ahead and look at this. So this one doesn't give you near the amount of information that the previous one said. So it says calculate the pH of the following salt solutions. And so we have a 0.355 molar KClO3. So looking at this salt, which one's going to be the weak parent? Come from the weak parent. We have K plus, that would be potassium hydroxide, and then we have ClO minus. ClO minus is our weak parent. So when we set up our rice, we're going to end up with ClO minus plus H2O reacting to form HClO plus OH minus. All right, our initial concentration is 0.355. Doesn't matter. 0, 0. So this is minus X plus X plus X. All that we should be able to do without really thinking. So we have 0.355 minus X. We are going to assume that it is, we're going to assume that it's less than 5%. And so this is X, and this is X. Now, we need to solve for X. Problem is, we are not given a Ka or a Kb. So what we need to look up, we need to look up the Ka or Kb of this, and I'm going to tell you that we are going to be able to get a Ka but not a Kb. So we're going to be able to get a Ka of HClO. So look in your tables, and I think it is the table that's under problem 19 that has it. It's kind of hard to see, but you need to find HClO, or another way that it might be written is HOCl. Right here. Yes, 3.5 times 10 to the negative 8. So is that, look at the top of the page, is this a Ka or a Kb? It's a Ka. So we're going to take that number and set it up in our equation. Come here. So we have Ka, and I need to go ahead and Ka is equal to HClO OH negative over ClO negative. So Ka was 3.8 times 10 to the negative 5. And again, before I go forward, does everybody know where I got that number? From the table. All right. And then, so this top part is going to be x squared. And then the bottom, we are just using the original concentration. We are trumping our x. 355. So x is going to be equal to concentration of OH negative, which equals what? I got 3.18 times 10 to the negative 4.00. Let me verify my answer as well. So, did I say 3. It's 3.5 times 10 to the 8, not 3.8. 3.5 times 10 to the 8. I just inverted some numbers. Delete second E negative 8 times 0.355 equals second square root, second answer. I get I'm not getting the same number. So 3.5 E negative 8 times 3.355 gives you 1.24, or yeah, 1.24 times 10 to the negative 8, right?
Yeah.
And then you just take the square root of that, correct? All right.
Yeah, I'm putting a negative to the negative 5 on the negative.
So did you get 1.11 times 10 to the negative 4? Yeah, that's what I got. I don't know. I'm looking at my work earlier. I got 3.18 times 10 to the negative 4 earlier, so I'm wondering what I did wrong. All right, I think I just went blank, or I did something twice. All right. So from there, what is it asking? It's asking us to calculate the pH. So when we plug in the pH, that would be the negative. We can get the POH first. Equals negative log of 1.11 times 10 to the negative 4. And then we can get pH from that. So we'll get POH and pH. So what do we come up with POH? I got 3.95. All right, and then that means that 14 minus that should give us 10.07, correct? Or 10.04, sorry. Yeah, 05. I just looked at the wrong number. All right. So looking at the last one here, let's go ahead and break this down. So we have NH4 and Cl. So when we break this up into its roots, we would be getting NH4 ion, which is positive, and chlorine ion, which is negative, right? Which one of those is coming from the weak parent? Chlorine's coming from HCl. This is coming from ammonia, right? So this is going to be our weak. So our Rice table is going to be our original concentration is 0.777. That's 0, that's 0. Minus X, plus X, plus X. I'm going to trump my X. All right, so now I need a Kb for ammonia, NH3. So I'm going to go to my tables. Is it on that last page? Yeah. All right. All right, so I go ahead and I find my ammonia. So it is, I'm thinking that is 1.8. We solved for it yesterday. It's 1.8 times 10 to the negative 5, I believe. That's a 5. I'm going to get y'all a cleaner copy of these tables. All right, so Kb of ammonia is equal to 1.8 times 10 to the negative 5. So that means that we can't go directly from Kb to Ka, or we can go directly, but we have to set it up. So we're going to go 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5 equals, and then we're plugging in our things. So it's going to be x squared over 0.777, which means that x equals the H plus concentration 2.08 times 10 to the negative 7. That's what I got. And then we can go directly from there to pH, negative log of that. Gives us a pH of 4.68, right? If we take the negative log of this number, that's going to give us our pH because we're already in hydronium here. This should be 10 to the negative 5, not. Unless, let me try it another way. Negative log 2.08. Let me see what happens there. Second in. Yeah, I still get 4.68. All right, let's look at two more real quick. All right, so C, I told you there's not going to be a calculation on this. Why won't we have a calculation on this? Parent of this is K, which is K plus. The parent of this is Cl minus. They're both strong. So I would just say this one does not undergo Hydrolisis because both the acid parent and base parent are strong. Yep, but you're not ever going to see that. Yep. All right. So you should be able to do D on your own if you want to give it a shot. I'm not going to do that one with us right now. What I will do is pass out